Good afternoon, students. Here in the model 3 design of a transformer today we'll discuss three more bits. So one, it is overall dimensions of the transformer, and one more bit, it is the estimation of a no load current of a transformer in the single phase transformer, as well as the in case of a three phase transformer also. So these are the three bits we are going to discuss in today's session itself. So first, let me start with the overall dimensions of the transformer. See here. So this is the overall dimensions of a transformer, means there are main two dimensions are there. So this is the first, we'll have a brief introduction about this one. The main dimensions of the transformers are, there are two main dimensions. One, it is the height of the window, and the second one, it is width of the window. Window, as I've already discussed in the previous session, what is window? Window, it is nothing but the space for the accommodation of primary winding as well as the secondary winding. So the main dimensions means the height of this window and the width of the window. Apart from these two main dimensions, some other dimensions also we need to calculate. So what are those? The first one, it is width of a largest stamping. Width of a largest stamping. The first one, it is A. Here it is represented here. Width of largest stamping, it is represented by A. It is. The stamping means what it is? Stamping in the sense that a transformer, it is provided with the laminations. What purpose we are going to be provided the lamination means, in order to reduce the thin sheets of laminations, we have to provide it to the core itself in order to reduce the eddy current losses itself. So stampings are nothing but a transformer laminations that has been cut out, that lamination that has been cut out of a strip or a sheet of a metals by punching or a punch press method or any kind of a method itself. Those are going to be called it as a stampings. Getting my point? So this A represent what's width of a largest stamping. So next one, what it is there? Second, another dimension, the diameter of a circumscribing circle, that is represented by what? Small d. Here it is there in the diagram. The width of, see here the diagram, so this diameter of the circumscribing circle, that is represented by a small d. One more capital D it is there. Don't get confused with these two terminologies. Small d means that is the diameter of a circumscribing circle, and a capital D is the, capital D, it is nothing but the distance between the two adjacent limbs, or also it is going to be called it as a distance between the, this is the core, it is there, distance between the two core centers, that is represented by capital D, or also distance between the two adjacent limbs it is. Getting my point? After this, so next dimension, which one it is there? That is the height of a yoke. So what is yoke? Anybody can tell? So see here, the height of the yoke, it is nothing but, yoke means what? Yoke are nothing but the sections of the core. Yoke, it is nothing but the section of a core which joins the limbs together. Nothing but what is the function of this yoke? Yoke, it is nothing but the one of the section of a core. It joins the limbs together. Limbs in the sense that in case of a single phase transformer, there are two limbs will be there. Here there are two limbs are there. Next thing it is, in case of a three phase transformer, there will be a three limbs will be there. Central limb will be there. So in case of a single phase transformer, two limbs are there. In case of a three phase transformer, three limbs are there. Yoke, it is nothing but what? Yoke, it is a section of a core which joins the limbs together. Getting my point? So that next thing it is here, HY represents what? It is a height of a yoke. So next thing it is depth of a yoke. Here it is, they have not represented here. Here it is DY. DY, it is nothing but here depth of the yoke. This depth of the yoke will be equal to the width of a, this is nothing but what? Here it is the space. So this is depth of the yoke. Depth of the yoke, it is represented here. So that will be nothing but the width of a largest stamping. So next dimension, it is overall height of the transformer frame. The overall height of the transformer frame, it is represented by capital H it is. Overall height of the transformer frame, it means altogether it includes core section, window section, and in this window primary winding and secondary winding will be there. So all together it is going to be considered as a transformer frame it is. The height of this transformer frame, it is represented by what? Capital H. Next thing it is, this capital W, it is nothing but the width of a transformer frame. So these are the terminologies what we are going to be representing now. So I hope you all of you Clear with this concept? So these are the dimensions we are going to be determining now for a various types of a transformer. Various types of a transformer in the sense that either it is a core type transformer or it is the shell type transformer. So these dimensions, whatever these above mentioned dimensions, we are going to be discussing now with respect to the different kinds of a transformer. One, it is core type, and one more, it is the shell type transformer. So first, in core type, there are two in the core type itself. First one, I will consider it as a single phase core type transformer, and second one, it is a three phase core type transformer. First in the core type, single phase, three phase, and in case of a shell type transformer, single phase, shell type transformer also I am going to consider for determining these overall dimensions of the transformer itself. Okay, shall we start with the first, that is single phase transformer, that is core type. So this diagram represent what? So this diagram, it is nothing but the vertical as well as the horizontal cross section view of a core as well as the winding assembly of a single phase core type transformer it is. Getting my point? From this figure, we will get a very important relationship. So these relationships are very important while solving the problems itself. So these formulas are, or these relations are very important while solving the numericals. Getting my point? So see the diagram and just let me know. So the first thing, it is capital D, it is there. Capital D means what I told here? Capital D, here it is a representation. It is nothing but distance between core centers, or it is also going to be called it as distance between the two adjacent limbs. So that is represented by capital D. Getting my point? How will write now? Capital D is, just I will zoom it here. See here, capital D will be equal to small d plus WW. So this will give the distance between the two core centers. Nothing but distance between the two core centers. It will be the sum of D plus WW. So only one limb I am considering here. So this capital D will be equal to small d plus WW. So next thing it is. So next, dy it is nothing but depth of the yoke. So depth, the height of the yoke it is. So here this will be depth of a yoke. Depth of this yoke will be equal to what? This A. Nothing but A, it is nothing but width of the largest stamping. Second one, it is clear. Depth of the yoke will be equal to width of the largest stamping, that is small a. Next, third one, it is capital H. Capital H, it indicates what? This capital H, it is the overall height of this transformer frame. How will write this one? A capital H is equal to HW plus HY plus HY. Nothing but what? HW plus 2HY. This will give the height of the transformer frame. So that is the reason I had written it as a capital H is equal to HW plus 2HY. So see here, capital H, this will be equal to height of the window plus height of the yoke, 2HY. Next, what it is there? Overall height of the transformer frame we had taken. Next, what is remaining? Overall width of a transformer frame. So overall width of a transformer frame, that is W. So we'll see this section. So this capital D means the width of this is nothing but the distance between the two core centers. Just you take a projections here. So capital D up to this portion, capital D plus A. So this will give the overall width of a transformer frame it is. So how will write now? Capital W is equal to capital D plus small a. Nothing but width of largest stamping. So these are the very important relationships with respect to what? Single phase core type transformer. So much difference. So next thing it is. So this is all about what? Single phase core type transformer. These are the overall dimensions we have got it from the this figure itself. So, okay, next shall I move on to the three phase core type transformer? So next thing it is, in case of a three-phase core type transformer, so how many limbs will be there? There are three limbs I told here. There are central limb will be there. One limb second, and this is third. There are three limbs are there. So now, so D, capital D means what? This is the capital D here. This capital D with respect to only one limb I am going to considering now here. So this capital D is equal to, capital D it is nothing but what? Distance between the two core centers or distance between the two adjacent limbs itself. So this d will be equal to one limb only I will consider for writing the relation. So small d plus ww. So that is only I had written here, small d plus ww. Next, depth of the yoke, it is nothing but what? So depth of the, this is the height of the yoke, nothing but have shown here, height of the yoke. Then depth of the yoke will be this one, height of the yoke. This is depth of the yoke will be equal to the width of a largest stamping, that is small a. Next thing, it is overall height of this frame. How will write now? The overall height of this frame, nothing but capital H. So this inside HW will be there, plus HY, nothing but HW plus 2HY. One HY is here, HY, one more here. So this, it will be a height of the window, HW here, HW plus HY, nothing but H is equal to HW plus 2HY it is. Next, overall width of this transformer frame. So here, so how many? So from this distance between two adjacent limbs, how many are there? Capital D plus capital D. From this vertical projection you take it here, D plus D, that is nothing but D plus D, 2D plus width of the largest stamping. So don't get confused with the relationship while solving the numericals. These are very important. In the problem itself, they are going to be mentioned initially single phase as well as the three phase. If they are mentioned in the question, how they are going to be mentioned in the sense that, for example, determine the overall dimensions of a single phase core type transformer. Overall dimensions means height of the window as well as the width of the window. These are the main dimensions of. So in case overall dimensions, if they have asked in the problem means, so these are the dimensions we have to write it here. So these are the things we have to determine. We have to find out if they in the problem, if they have asked overall dimensions of a single phase transformer means, these four relations we have to find out it now. So the basic difference, very easy to remember these formulas. In case of a single phase transformer, first three bits are same, capital D, dy and H. All three are same, and only W, it is nothing but the overall width of a transformer frame. Here it is D plus A. In case of a three phase transformer, overall width of a transformer frame, it is 2D plus A. This is the only change. In case of a three phase transformer, it will be easy to remember the formulas itself. So this is what, these are the dimensions for the three phase core type transformer. Okay, next we'll move on to core type. It is over. Next thing, it is in case of shell type transformer. How will write here? In case of a shell type transformer, depth of the yoke. Depth of the yoke, it is nothing but this one. So the depth of the yoke, it is nothing but the, this is small b itself. Depth of the yoke will be represented by a small b. And the height of the yoke, it will be equal to the width of the largest stamping. It is HY is equal to A. Next thing, it is width of this transformer frame. It is how many WWs are there? WW width, it is nothing but this one. Overall width of this transformer frame. See here, below also they have shown here. So width of this transformer frame. So this is capital W, indicates that width of this transformer frame it is. So this will be the sum of WW plus how many stampings are there, you just check it. So here 1A plus 2A plus one more A, altogether it will be 4A. So that is the reason overall width of this transformer frame, it will be 2WW plus 4A's, 4A, that I had written here. Then what about overall height of this frame? This is HW plus A, one more A, nothing but 2A's itself. H is equal to HW plus 2A. So these are the very important relationship. So when solving the problems, you need to remember all these formulas. Basically in the problem itself, in the numericals itself, they are going to ask, they will mention it very much clearly. In single phase transformer, single phase core type transformer, if they asked to determine the overall dimensions means, just you find out by making use of these formulas, you just find out all these dimensions. In case of in problem, in three phase core type transformer, overall dimensions if they asked means, so these are the relationship we need to find out. In case of a shell type transformer, if they had asked means, these are the four relationship we need to determine it. Now just you remember all these relationships or a relation or the formulas from the while solving the numericals. These are very important itself. So this is all about what? Overall dimensions of a transformer itself. In various transformer, whether it is single phase transformer and one more it is three phase transformer. Single phase, three phase with respect to core type we have discussed, as well as the shell type transformer also we have we get the some relationship also. So this is all about overall dimensions of the transformer. Okay, next shall we move on to estimation of no load current of a transformer in case of what? Single phase core type transformer. Getting my point? So shall I start with this one? Okay, let me start how the estimation of no load current of a transformer in case of a single phase core transformer it is going to be done. Let me start. So see here. So first what it is there here, the no load current of a transformer. The no load current of a transformer, it has two components. The first component it is magnetizing component and the second one it is loss component. So what is this magnetizing component? So this magnetizing component it is nothing but magnetizing current, that is represented by IM it is. So this magnetizing current will be depends upon the MMF required to establish the desired flux. So this magnetizing current depends upon the MMF required to establish the desired flux. This MMF it is nothing but what? MMF it is nothing but the ampere turns it is. So getting ampere turns. So this ampere turns helps to establish the desired flux it is. So this IM will be depends upon the MMF. First point it is clear. So second component is loss component. The loss component of a no load current, that will be depends upon the iron losses here. So iron losses means it is also going to be called it as a constant losses. So these constant losses are of a two types. One it is a eddy current loss it is there. One more it is the hysteresis loss it is there. I hope you are getting this one. So what I am telling here, the no load current of a transformer, it has the two components. One it is the magnetizing component and one more it is the loss component. And this magnetizing component or the magnetizing current, it will be depends upon the MMF. MMF it is nothing but the ampere turns ampere turns required to establish the desired flux here. And the loss component will be depends upon the iron losses. So iron losses are also going to be called it as a constant losses itself. The constant losses in the sense that either it is a eddy current loss or hysteresis loss itself. Getting my point? Okay, let me start with the derivation here. So this diagram, it represents the single phase. This diagram represents what? Single phase core type transformer it is. Single phase in the sense that only one window will be there. So the window it is nothing, it is a space for the accommodation of a windings it is. Getting my point? So see here, from the figure, let me make it zoom here. So see here, so this from this figure, total length of a core. Total length of core means LC stands for what? L it is a length, C stands for the core here. So LC it is nothing but length of a core. Then total length of core, how will write here? LC plus LC. So that will be 2LC. Getting my point? Next thing it is LY represents what? Length of a yoke it is. Yoke means what? What I told here? Yoke it is also a section of a core which joins the limbs together. Getting my point? So this your total length of the yoke will be Ly plus Ly. Then how much it will be? So this will be 2Ly. Getting my point? So first we have written this down. I hope you are getting. Total length of the core it is 2LC. Total length of the yoke will be 2Ly. So clear. So next thing it is. So see the diagram. See here, LC, length of the core. Shall I write it? It will also be equal to the height of the window. So this LC, it is also equal to the height of this window. Then what about LY? This LY, it is nothing but also equal to the width of a window. So LC, length of the core, it will be equal to the HW or nothing but height of the window here. LY, it is nothing but it will be equal to the WW, nothing but width of window. I hope all of you are getting this one, how I had written. So next thing it is. Next what I told here, we are deriving the equation for the no load current. There are two loss components are there. One it is magnetizing component, one more it is loss component. Is it right? These are the two components we are doing. The first component, that is magnetizing current, that is depends upon the what? MMF itself. Then how many here core section it is there, one more yoke section it is there. So that is the reason first MMF for core I will consider. After this MMF of the yoke I will consider. Then we will combine both. Then you will get the total total magnetizing MMF. Hope you are clear about this one. The first, let me start with, first we'll take one. First, in order to determine the first magnetizing component, that is magnetizing current, it depends upon the MMF. So MMF I am going to be determining with respect to the core as well as the yoke section here. The first one, it is MMF of core. So how we'll write this one? MMF of the core. See here. MMF of core, it will be the product of MMF per meter for a maximum flux density in the core into total length of a core itself. So how we had written here? MMF means ampere turns. So how we had written here? Small a, ampere, T in the sense that turns, C stands for what? Core. MMF per meter for a maximum flux density in the core. So nothing but ampere A, number of turns it is T in the core. That is why I had mentioned it as a C itself. ATC. Ampere turns in the core, nothing but it is MMF into what it is, the total length of a core. Total length of a core means what is there? Total length of the core, it is 2LC. See the equation number 1. So I had written here into 2LC here. Then altogether it will be 2ATC LC. Call this equation as 3. So core section it is over. Then which section it is remaining? Yoke section. Then MMF for yoke, it is also the product of MMF per meter for a maximum flux density in the yoke into total length of the core here. So here MMF means ampere turns. Ampere turns in yoke it is there. That is the representation of Y. Y it is nothing but yoke. MMF in yoke. ATY into total length of a yoke. Total length of a yoke, it is how much it is there. See the second equation here. Second equation is total length of the yoke, it is 2LY. So I had substituted here into 2LY. Then altogether it will be 280Y LY. Call this equation as a 4 it is. So getting my point? Next thing it is. So next what we have to add these two, MMF for the core as well as the MMF of the yoke. Then we will get the total magnetizing MMF. That will be helps to determine the magnetizing current. Getting my point? The first component, the magnetizing component, it depends upon the MMF. That is the reason. Getting my point? Total magnetizing MMF, I will represent it as a capital because it is a total 80 naught, nothing but at no load. Getting my point? 80 naught. So this will be the sum of what? MMF for core, MMF for the yoke, plus along with the MMF for joint section. Nothing but core as well as the yoke section. It is going to be, sorry, I had written here MMF of the core plus you make it MMF of the yoke it here. So I had written both the sections as a core only. So that is the reason. MMF for core plus MMF for yoke it is plus MMF for joint it is. Then you substitute here. What is the MMF for the core? 280CLC. Then what is the MMF for yoke? That is 280YLY. Then MMF for the joints you write as it is. So call this equation as a 5 it is. So next thing it is. So next what we are going to deriving now? MMF. MMF it is nothing but magnetizing current depends upon the MMF here. So magnetizing current, how we have to write it now? The maximum value of the magnetizing current. So that will be equal to this 80 naught divided by TP. Why I had taken only primary terms in the sense that, see here, the magnetizing current is a term used to denote the, see here what I had written, just for your sake of clarification purpose, I had written here, the magnetizing current is the term used to denote the total amount of a current that flows into the primary of the transformer. So total amount of the current which is flowing in the primary of the transformer. When it will be flowing? When the transformer it is going to be gets energized at a specific voltage as well as the frequency with the secondary open circuited. Getting my point? Secondary it is open circuited. That is the reason no load. So load, secondary side will be, load will be connected, but no load in the sense that secondary will be open it is. So the only in the primary winding itself, The current will be starts flowing when the transformer it is going to be energized at a specific voltage as well as the frequency. That is the reason this magnetizing current will be flowing in the primary winding itself. So that is the reason the primary number of turns only I had taken here. 80 naught divided by TP. This will give the maximum value of a magnetizing current. That is IM. Getting my point? I hope you are getting these things. So next we'll move on to, so whatever the magnetizing current we got. So suppose if there are two cases are there. Suppose if the magnetizing current is sinusoidal. If the magnetizing current is sinusoidal, then we'll take it as a RMS value of the magnetizing current value. Sinusoidal means RMS value of the magnetizing current will take, that is IM is equal to, RMS value means divided by root 2. 80 naught divided by root 2 it is. Root 2 TP. So suppose if this magnetizing current it is non-sinusoidal, then what to do? So this root 2, instead of this root 2, it is going to be replaced with the help of the peak factor, that is Kp. So how will write this equation? Im is equal to 80 naught divided by, instead of this root 2, what I am taking here? Peak factor. This is only in the case of when this magnetizing current it is non-sinusoidal. Then 80 naught divided by Kp into Tp. Instead of this root 2, I had taken here Kp. Only with respect to when the magnetizing current is non-sinusoidal. Getting my point? So this will give the magnetizing current IM we got. Then which component is remaining now? One more component, it is loss component. The loss component of no load current is, that is power. What is the formula for power? Nothing but a iron loss. P is equal to V into I. Is it right? With respect to primary, I will take current. It is represented by loss component. That is IL. It is no load current. It is loss component current. So see here. So from this equation, P is equal to V into IL. So from this equation, I can write it for the IL now. IL is equal to PI divided by VP. So this will be you the loss component of a current, no load current. So PI it is nothing but iron loss in a watt it is. VP it is nothing but the terminal voltage of the primary winding. So we'll get it now from this equation. We'll get the loss component of a no load current. So then what we got? Already magnetizing current we got, as well as the loss component of the current we got. Then what is the formula for no load current? No load current will be represented as a I naught, that will be equal to root of Im square plus IL square. So getting this one, how we have derived this equation? This is the estimation for the no load current of the transformer. Which transformer? Single phase core type transformer. I hope all of you are clear with this concept. Shall I move on to estimation of a no load current of a 3-phase transformer? Okay. So the next we'll discuss it on the estimation of no load current of a transformer, that is 3-phase core type. So okay, see this one. This is also very much easy. Only small difference is there between single phase as well as the 3-phase here. See the diagram here. So here in this diagram, how many windows are there here? This is the 3-phase core type transformer. So 3-phase core type transformer means there are 2 windows are there here. So first window and this is the second window. In this windows only the windings will be placed here. Is it right? Window it is nothing but the space for the accommodation of a primary winding as well as the secondary winding it is. Getting my point? So next let me start the derivation with respect to the 3-phase transformer. So first one it is total length of a core. Total length of the core it is, how many LCs are there here? LC plus LC plus LC. Then total length of the core will be 3 LC. Then what about total length of yoke? So 1 LY it is there. This is the length of a yoke and this is the length of a yoke. Nothing but LY plus LY. This will be 2 LY. So total length of the core is 3 LC. Total length of the yoke it is 2 LY. Correct? So next what it is there? LC it is nothing but length of the core. Length of the core will also be equal to what? See here, same it is. Height of the window. Then what about this one? Length of the yoke. Length of the yoke will be the sum of width of the window, width of the window. Nothing but LY is equal to 2WW. Nothing but width of the window. Overall it is there all together. Width of the window, width of the window. LY is equal to 2WW I had written here. So next thing it is, so what I told in the previous derivation itself, the no load current of a three-phase transformer, it is consist of the two components. It is one, it is the magnetizing component, and one more, it is the loss component. This magnetizing component, it will be depends upon the what, MMF. So MMF of the which sections we have to consider it now? One, it is for the core section, one more it is for the yoke section. It is, so okay, see here, MMF for yoke here. So MMF for core, how will write it now? MMF per meter for a maximum flux density in the core into the total length of a core here. So MMF per meter, MMF means ampere turns, ampere I had taken here, turns I had taken here, C stands for what? In the core, MMF in the core ATC, then to total length of the core. Total length of the core, how much it is there? 3 LC. So that only I had written it here. So altogether it will be 3 ATC LC. Call this equation as 3 itself. The first MMF for the core section, it is over. Then which section it is remaining now? MMF for the yoke. So this MMF for yoke, see here, in MMF for yoke, it is also a product of MMF per meter for a maximum flux density in the yoke, not in the core, okay, into total length of a yoke here. So how will write it now? MMF ATY. MMF means ampere turns in the yoke. That is the why here represented here. Total length of a yoke means what? Second equation, what it is there? Total length of the yoke, it is 2 Ly. That is only I had substituted here. Then all how much you will get it here? 280 Ly. Call this equation as a 4 it is. Once we determine the MMF for the core section as well as the yoke section means, then what we have to do? Then total magnetizing MMF. So that is nothing but 80 naught. It will be the sum of MMF for the core as well as the MMF for the yoke, and joining of these two MMF for the joints also we are going to consider here. The total magnetizing MMF at no load, how will represent? Ampere turns. MMF means ampere turns at the no load, not in the sense that it is at no load. So MMF for the core, how much you got? 3 ATC LC. See the equation 3 here. Then MMF for the yoke, it is 280 Ly. See the equation 4. That only I had substituted here. Then MMF for the joints I had written as it is. Okay. So next what it is there? This is the total magnetizing MMF in case of a three-phase transformer we are doing here. Per phase if you had taken means this 80 naught will be equal to 3 ATC LC plus 280 Ly plus MMF for joints divided by 3, because it is per phase I am going to be considering now here. Getting my point? Hope all of you are getting here. So next bit what it is there, see here, this maximum value of magnetizing current, nothing but this 80 naught divided by TP. TP why I had taken here, just I wanted to once again I wanted to tell here, this magnetizing current, that is IM, it is the term used to denote the total current that flows in the primary of the transformer. So the total amount of the, in no load we are discussing now. In the secondary side only load it is going to be connected, but we are discussing now what it is, no load. There is no load, it is connected at the secondary side. Then what will happen? The secondary side there will not be a flow of a current. So only in the primary winding the current will be flowing here. So when current will be flowing, then when the transformer it is going to be gets energized. Once the transformer it is going to be gets energized at a specific voltage and frequency, the current it is going to be flows through the primary of a transformer with the secondary open circuited. That is the reason I had taken, because the current will be flowing in the primary winding itself. So the current will be flowing in a primary winding means the primary number of turns I had taken here, that is TP. So that is the reason the maximum value of magnetizing current will be equal to 80 naught divided by TP. So getting my point? After this, so this magnetizing current what we got, if it is sinusoidal, there are two cases I am going to considering now. The magnetizing current, if it is sinusoidal, then RMS value of the magnetizing current will take. So RMS value in the sense that divided by root 2 it is. So we got the equation for IM here, that is 80 naught divided by TP. The RMS value in the sense that 80 naught divided by root 2 TP. So only RMS value. Then if this magnetizing current, it is not sinusoidal, it is non-sinusoidal means instead of this root 2, what I have to take, what I am taking here, the peak factor. Instead of this root 2, we'll mention it as a Kp, nothing but peak factor. So nothing but Im is equal to 80 naught divided by Kp into Tp. Only in case of if the magnetizing current is non-sinusoidal. If it is non-sinusoidal means instead of this root 2, take peak factor Kp. So that I had taken here. We got the magnetizing component now. Then what one more component what is remaining? That is loss component. Is it right? So loss component is, see here, the loss component, let total loss component, how we are going to be determining now, it will be depends upon the what I told here, it will loss component, it depends upon the iron losses. Iron loss, it is nothing but the power loss, that is Pi. So the Pi will be give it as a what in case of a 3-phase, 3 VPIP or a 3 Vp, because loss component means that is the loss current, no load current, loss component current we are considering here, that is the reason represented as a IL here, 3 Vp IL. So from this equation I will get the loss component of the no load current, that is IL. So IL will be equal to Pi divided by 3 Vp. Hence no load current per phase, that can be written as a I naught is equal to I root of Im square plus IL square. So this is the derivation in case of what? 3-phase transformer, no load current of a 3-phase transformer. Hope all of you are getting these concepts. Okay, thank you.